Hi everyone, welcome back to the video series on Bitcoin. Generating a private key from a random number. The first and most important step in generating keys is to find a secure source of entropy or randomness. Creating a Bitcoin key is essentially the same as pick a number between 1 and 2256. The exact method you can use to pick that number does not matter as long as it is not predictable or repeatable. Bitcoin software uses the underlying operating system random number generators to produce 256 bits of entropy randomness. Usually the OS random number generator is utilized by a human source of randomness, which is why you may be asked to wiggle your mouse around for a few seconds. More precisely, a private key can be any number between 1 and n1, where n is a constant, n 1.1581077, slightly less than 2256, defined as the order of the elliptic curve used in Bitcoin. See elliptic curve cryptography on page 60. To create such a key, we randomly pick a 256-bit number and check that it is less than n1. In programming terms, this is usually achieved by feeding a larger string of random bits collected from a cryptographically secure source of randomness into the SHA-256 hash algorithm, which will conveniently produce a 256-bit number. If the result is less than n1, we have a suitable private key. Otherwise, we simply try again with another random number. The following is a randomly generated private key. K is shown in hexadecimal format, 256 bits, shown as 64 hexadecimal digits, each 4 bits. So here's that big long number string there. To generate a new key with the Bitcoin Core client, see chapter 3. Use the get new address command. For security reasons, it displays the public key only, not the private key. To ask Bitcoin to expose the private key, use the dump key command. The dump priv key command shows the private key in a base 85 checksum encoded format called the wallet input format, WIF, which we will examine in more detail in private key formats on page 70. Here's an example of generating and displaying a private key using these two commands. $sign Bitcoin CLI get new address 1J7 MDG5 or BQYUHENY do DX39 WV WK7 FSLPEOX S Bitcoin CLI dump priv key 1J7 MDG5 or BQY UHENY DX39 WVWK7 FSLPEOX KXFC1 JMWWCOACICAW Z3EXA96M BM6TB3 TYZGM F6YWGD GWZGAWV. The dump priv key command opens the wallet and extracts the private key that was generated by the get new address command. It is not possible for Bitcoin to know the private key from the public key unless they are both stored in the wallet. You can also use the Bitcoin Explorer command line tool to generate and display private keys with the command seed EC new and EC2WIF. Hash sign BX SEED BX ECNEW BX EC2WI 5J3 MBBAH 58CPQ3Y5 RNJPUKPE62SQ5T FCVU2J PBNKEYHFSYB1. Public keys. The public key is calculated from the private key using elliptic curve multiplication, which is irreversible. K equals KG, where K is the private key, G is a constant point called the generator point, and K is the resulting public key. The reverse operation known as finding the discrete logarithm calculating K, if you know K, is as difficult as trying all possible values K, i.e. a brute force search. Before we demonstrate how to generate a public key from a private key, let's look at elliptic curve cryptography in a bit more detail. Elliptic curve cryptography is a type of asymmetric or public key cryptography based on the discrete logarithm problem as expressed by addition and multiplication at the points of the elliptic curve. Figure 4.2 is an example of an elliptic curve similar to that used by Bitcoin. Bitcoin uses a specific elliptic curve and a set of mathematical constants as defined in a standard called SECP256K1, established by the National Institute of Standards and Technology (NIST). The SECP256K1 curve is defined by the following function, which produces an elliptic curve y equals x3 plus 7 over fp, or y2 MODP equals x3 plus 7 MODP. The MP modular prime number P indicates that this curve is over a finite field of prime order P, also written as AP, where P is equals 2256 232 29 28 27 26 24 1, a very large prime numbers. Because this curve is defined over a finite field of prime order instead of over the real numbers, it looks like a pattern of dots scattered in 2 dimensions, which makes it difficult to visualize. However, the math is identical to that of an elliptic curve over real numbers. As an example, figure 4.3 shows the same elliptic curve over a much smaller finite field of prime order 17, showing a pattern of dots on a grid. The SECP256K1 Bitcoin elliptic curve can be thought of as much more complex pattern of dots on an unfathomably large grid. So for example, the following is P, which coordinates x, y. This is a point on the SECP 256K1 curve P. So P equals all these large numbers here. Example 4.1, using Python to confirm that this point is on the elliptic curve, so you can see that there yourself. In elliptic curve math, there is a point called the point of infinity, which roughly corresponds to the roll of 0 in addition. On computers, it's sometimes represented by x equals y equals 0, which doesn't satisfy the elliptic curve equation, but it's an easy separate case that can be checked. There is also a plus operator called the addition, which has some properties similar to the traditional addition of real numbers that grade school children learn. Giving 2 points P1 and P2 on the elliptic curve, there is a third point P3 equals P1 plus P2 also on the elliptic curve. Geometrically, this third P3 is calculated by drawing a line between P1 and P2. This line will intersect the elliptic curve in exactly one additional place, called the P3 equals x, y. Then reflect on the axis to get P3 x minus y. There is also a couple of special cases that explain the need for a point at infinity. If P1 and P2 are at the same point, the line between P1 and P2 should extend to the tangent on the curve at this point P1. This tangent will intersect the curve in exactly one new point. You can use techniques from calculus to determine the slope of the tangent line. These techniques curiously work, even though we are restricting our interest to points on the curve with two integer coordinates. In some cases, i.e. if P1 and P2 have the same x values but different y values, the tangent line will be exactly vertical, in which case P3 equals point of infinity. If P1 is the point of infinity, then P1 plus P2 equals P2. Similarly, if P2 is the point at infinity, then P1 plus P2 equals P1. This shows how the point at infinity plays the role of zero. It turns out that plus is associative, which means that A plus B plus C equals A plus B plus C. This also means you can write A plus B plus C without parentheses and without ambiguity. Now that we have defined addition, we can define multiplication in the standard way that extends addition from the P point on the elliptic curve. If K is a whole number, then KP equals P plus P plus P plus P K times. Know that K is sometimes confusingly called an exponent in this case. Generating public keys. Starting with the private key in the form of a randomly generated number K, we multiply it by a predetermined point on the curve called a generator, point G, to produce another point somewhere else on the curve, which is the corresponding public key K. The generator point is specified as part of the SECP 256 K1 standard and is always the same for all keys in Bitcoin. K equals K plus and G, where K is the private key and G is the generator point and K is the resulting public key. A point on the curve. Because the generator point is always the same for all Bitcoin users, a private key K multiplied with G will always result in the same public key K. The relationship between K and K is fixed but can only be calculated in one direction, from K so it's a capital K. That's why the Bitcoin address derived from capital K can be shared with anyone and does not reveal the user's private key K, which is lowercase. Implementing the elliptic curve multiplication, where we take the private key lowercase k generated previously and multiply it with the generator point G to find the public key capital K, and K equals capital K equals 1E99423A4ED2760 A8, A15, A26, 16, A2B0E 95E, CED 330, AC 530, EDCC 32, C8FF C6A 526A EDD. Public K key is defined as point K equals XY, K equals XY, where X equals F0 28892 BAD 7ED 57D 2FB 57B F330 81D 5C FC F6F 9ED 3D 7F159 C2E2 FFF 579 DC3 Y equals 07CF 33 DA18 BD 734 C600 B96A 72 BB C 474 9D 5141 C 90 E C8 A C328 A E52 DD FE 2E50. To visualize multiplication at the point with an integer, we will use the simpler elliptic curve over real numbers. Remember that the math is the same. Our goal is to find multiple k g of the generator point of g, which is the same as adding g to itself. K times is now in a row. In elliptic curves, adding a point to itself is the equivalent of drawing a tangent line on the point and finding where it intersects on the curve again, and then reflecting that point on the x-axis. Figure 4.4 shows the process of deriving g, 2g, 4g as a geometric operation on the curve. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.